Greetings everybody. Let's take a look at the converse of the fundamental theorem of line integrals. And so kind of what we've got at this point is this setup, that we've got this notion of a conservative vector field, so you're the gradient of some function. From Clairaut's theorem, that says that if we take the curl of a conservative vector field, that one was going to be 0. And so then we've had our fundamental theorem for line integrals that said, all right, if this thing was conservative, then our fundamental theorem of line integrals said that this thing was going to be path independent. And so now we've got a couple of other kind of things that show up in this. We had this notion of if something was irrotational, was it guaranteed to be conservative? And if we're irrotational, how does that come into play with path independence? And then the question that we left off with our fundamental theorem of line integrals video was, what about the converse? If we're path independent, are we guaranteed to be a conservative vector field? Well, this one is the one that we'll try to answer in this video, and coming up in a video or two from now, we'll talk about Green's theorem to kind of answer this question. What's the behavior of an irrotational vector field with respect to path independence? How does that work? And so for the converse of the fundamental theorem of line integrals, we say that F is a vector field that's continuous on an open path connected region D. And so the question that we want to answer, if we are independent of path in that region, does that guarantee that our vector field was going to be conservative? Well, the idea goes something like this. Since D is going to be a path connected region, we can choose any old point in D as kind of our starting point. Path connected means that we can get from any 2 points in that region by some kind of path. And so if we want to evaluate our function, if we want some maybe potential function q, how do we get it? Well, we define this potential function f of q for the point in D as just being the integral over c of f dot dr, where c is going to be any old path that we want from p to q. Now, because we have the assumption that this thing is path independent, it doesn't matter which curve that we choose. We're going to get the same answer either way. And so that's why this function is really a well-defined function, because of our assumption of path independence. Since D is open, then it means that we can put a little open ball around this point Q and kind of keep that thing inside D. That little open ball is going to be important because if we want to show that the partial of this function that we introduced with respect to x is our first component, then inside this little ball, we want to choose a path gamma that only changes in the x direction. So if q is this point that we're interested in, it's x, y, and z, then we want a path that's maybe something similar to our y value stays the same, our z value stays the same, and we're only changing our x value for some sufficiently small region that keeps us inside this open ball around Q. And so the idea, let's call this path C1. So this is our constant horizontal path, constant path in the x direction. We'll call that one C1. And for C2, well, let's just pick any other point on that curve C1 and say, well, let's just run another path C2 from P up to this kind of arbitrarily, randomly chosen point R that's on this constant path C1 that's inside this open ball. And so our curve C, that we can take any curve that we want to. So let's say C is going to be C1 plus C2. So our arbitrary curve over to R1, and then our constant curve inside that ball over to our point Q. And so f of x, y, z, we can split that up as the integral over the first curve plus the integral over the second curve. Now remember this point R that we chose, that thing is not dependent on Q. There's no functional dependence for any of those values that we have in there at all. R was totally arbitrary. The only thing that we needed was it was a point on that curve that was inside the ball. Didn't depend on Q other than not being Q itself. And so since that thing is independent of our point Q in particular, it's independent of the X value that Q actually holds. And so if we take the partial derivative of f with respect to x, then since that thing didn't depend on x, that line integral is going to be 0 because it's just a constant for that thing. And so our partial with respect to x is only applied to our second function. Well, if we kind of write those out, remember those component functions were p dx, q dy, and r dz. Now is where our particular curve C1 comes into play. Y and z were constant on each one of those. And since they were constants, in particular, that means that when we would compute dy and dz, we get 0 on those things. And so what happens, this first component, that one disappears, q dy disappears, r dz disappears, and we are just left with that the partial of f with respect to x is going to be the derivative with respect of the integral with respect to x. Well, that's our fundamental theorem of calculus, and that tells us it's just the integrand p. Now, I can kind of go back and say that, you know what, this argument really didn't have anything in particular to do with x. We could choose a path that was constant for everything but y. We could have chosen a path that was constant for anything with z. The argument's still going to go through. Everything's still going to be the same. But we would get that the partial of f with respect to y was going to be q, and the partial of f with respect to z was going to be r. And so what that means is that f is going to be the potential function for f, and so that f is the gradient of this little f that we computed. And so kind of another way of looking at this is that kind of coming back to this diagram of our conservative property, that it's the gradient of some function, that's going to be equivalent to this thing being path independent for the fundamental theorem of line integrals. Path independence really just means that the line integral, if we put a little circle around our line integral, that's kind of a notation saying that we're integrating over a loop. So the circle around the integral sign just means that, okay, my curve is just going to be a loop. So the integral over loops is going to be 0. We had, if we were conservative, Clairaut's theorem tells us that we're irrotational, and so that the curl of our vector field was going to be 0. And what we just showed now, fundamental theorem of line integrals go this way. We just proved the converse, and so our fundamental theorem of line integrals, a little bit like our fundamental theorem of calculus, has those two parts to it, and they go both ways. And so we've almost gotten all of the components that we need for this particular diagram. The only thing that we're missing is Green's theorem, and so stay tuned for that one. And I will see you guys